the floor for your presentation.
Okay, thanks, Xavier. So yeah, I changed a little bit the title, but basically it's the same thing. So yeah, sure, thank you. So so first of all, I would like to express my gratitude to the Open Sky community, which has helped me a lot. And yeah, it's my honor to speak here, to be invited to speak here. So the topic of my talk is gradient-based smart predict and optimize framework for aircraft arrival scheduling problem inside terminal maneuvering area. So yeah, it's a very long topic, but basically like smart predict and optimize is a concept, it's a new framework that proposed by computer science people, management science people, and then I just try to do a exploratory research, applying it into this area, which is aircraft arrival scheduling problem, try to see what it can do and do a little bit about the research. So yeah, first of all is some background information that air transportation faces challenges with increasing demand. The problem will still exist post-COVID-19, as we can see from the left figure, that the total passengers carried worldwide is increased exponentially since 1980s. Even though the COVID-19 has affect this trend, but actually, as you can see from the right figure, the global RPK in November 2023 is actually almost reached the same level as the pre-pandemic level. So it tells us that the problem will still exist post-COVID-19. So, and for all the phases, terminal airspace is kind of the bottleneck of air traffic management because it has natural high traffic density and capacity. You need to handle arrival and departures. And compare with departures, actually arrival is more complicated because consider the competitive weather. If you are operating the arrivals, you might have this kind of holding, vectoring, go around, a lot of different non-standard operations. You need to mitigate your delays. But for departure, you can just simply maybe hold on the ground. You don't need to care about the fuel burn, something like that. So there are challenges for the arrival research inside the terminal airspace, but also there are potentials. So according to an article in The Economist, 5 to 10% of aviation fuel per flight can be saved if we have a better arrival operation for flights. Also, there are more higher accessibility and quality of flight-related data inside the terminal airspace, which is very understandable because it's closer to the ground and also more sensors around that area. And also, even you can maybe use some of the local detection instrument on the runway, such as gray vortex, particle detections to enhance your research. So that's why I call it there are challenges, but there are also potentials in this area. So to solve the problem, actually, since the 1960s, 1970s, a lot of researchers apply operational research tools, tries to formulate the aircraft arrival sequencing into a mathematical formulations using mixed integer programming and also heuristic, also dynamic programming as well. And since 2010, because of the increasing availability of the flight data, also thanks to Open Sky as well. So more and more machine learning methods has been applied in this area. So one of the key direction is the estimated time of arrival prediction, which you try to use the information you gather before the aircraft enters the terminal area to predict the time that one aircraft spends inside the terminal area. And another very interesting research, which I have also been involved in, is modeling the local weather impact on the air traffic performance. So yeah. But however, the gaps still remain. So that's why I try to propose this research here. So the first gap I want to identify is the integration of these machine learning driven prediction into optimization is have been relatively unexplored. Let's say most of the research is separate. You do fancy machine learning research, or you do fancy operation research study, but there's not much study that connects two things together. Or maybe you treat it as a two-stage approach, which I will explain in the next few slides. And the second gap I identify is the adverse weather condition is very hard to quantify in mathematical models. So actually, it's because it's a very infrequent type of scenarios according to the real world data. So like as an example, in Hong Kong, like almost maybe nearly just maybe 8% or 7% of the data are like bad weather. So you have like 92, 93% of data are good weather. So you're very hard to apply machine learning method to try to learn this kind of pattern because the data is like very, very infrequent. So yeah, I have an example here. So a study in 2021 from Michael and Samir actually shows that predicting the weather impact on arrivals are like harder than predicting the impact of weather on departures. And also, like from my study, I used imbalance sampling, which will definitely lose some of the data features. So, so go back to the first gap. I identified that this is like an illustration of the two-stage predict and optimize. So basically, like it's a very very easy to interpret. So, okay, yeah. So this part is the prediction part. So you're trying to train a prediction model using the predictive error, which is like mean square error and mean absolute error. You try to focus on the predictive error. So after you got the predictive value of the parameters, you try to fit in the optimization solver. So this is like, even though there are not much, but most of the study that combine prediction and optimization did like in terms of combine these two things together. So what I try to do here is just to apply this framework called end-to-end predict and optimize framework. Also, you can call it like E2EPO. It tries to embed the optimization solver into a differentiable predictor, so by a decision loss. So this is particularly relevant for like aircraft arrival scheduling problem because you have fixed standard arrival routes and observable weather condition, but yet still you cannot like easily predict what happened inside the terminal area. The time will still be different. So yeah, so that's why I try to apply it. And in my study, I use this called Smart Predict and Optimize framework, which is like a subset of the E2EPO framework. So this is what I try to do here. And the objective of this work is threefold. First, I formulate the first as SPO framework for this problem, ASP problem within terminal area. And then I explore the potential of this framework in addressing the adverse weather concerns. So instead of using like weather factor as the input of the machine learning model, I try to use a different paradigm by just apply this framework. And the third thing is that I provide a case study at London Gatwick Airport. So yeah, next I will just elaborate a little bit more on the methodologies. So this is the general schematic diagram of the study. So basically, from left, we have like raw flight data, and then we do data preprocessing. We create the traffic instances, and then we just fit it into the so-called gradient-based SPO framework here. And the core framework components is the gradient train formula. So basically, you just need to compute the impact of you just wants to optimize the decision loss, tries to fine-tune the parameters of the prediction model. So this is the idea for these all math formulas here. And next, I will briefly introduce the optimization model I use, the aircraft arrival scheduling model. So basically, my model is based on a classical single runway aircraft arrival scheduling problem proposed by Beasley in 2000. So there are three decision variables. Yi refers to the actual landing time, and omega I is the binary variable indicating if aircraft I lands after its expected time, and delta ij refers to the sequence of aircraft I and j. And for the constraint, I would just like put like three key constraints here. So try not to confuse people. And basically, you need to have a feasible time window, which is like a early bound and a late bound. And also, because we are introducing omega, so we need a definition of omega. So we have a bit constant m tries to like constrain it to when yi is larger than ti, so that omega equals to 1. And then also we have like constraints to maintain the separation between aircrafts. And for the objective function, it's like rather simple. So we just try to minimize the sum of costs for all delay aircraft. So conventionally, delay cost, we need to have like these three components, which is the unit time delay cost per aircraft type, and predicted arrival time and expected arrival time. So actually, we do some simplification here, because we know that expected arrival time actually you know beforehand, before the aircraft enters the terminal area. And then also this unit delay cost is also predetermined by the aircraft type and also derived from operational cost study. So basically, I just simplify it. The cost will be directly equals to the predicted value of the arrival transit time. So after talking about the optimization model, I will also briefly just introduce what I have done like in the prediction. So one of the most important thing here is the traffic instance generation. So basically, traditionally, for estimated time of arrival prediction, you are predicting like each flight independently. So you use N features, including the flight data with, before it enters the terminal area, weather information beforehand, and historical pattern, and maybe traffic scenario, something like that. And the output is like a single flight duration, like TI. So, but however, in this framework, because you're trying to like compute the decision loss for each iteration, so that you need to consider the entire traffic scenario. So you can, if you just predict like individual flights one by one, it doesn't work. So how I do it, basically I just generate the traffic instance from the flight data. So you process N flights simultaneously as one traffic scenarios, and then you so the input dimension will become from N become N times M, and the outputs will become N cost for those number of aircrafts in one instance. And for prediction model, yeah, try not to complicate things. So here we use like two very simple differentiable predictor. One is linear regression, and the other one is multi-layer perceptron. So both of them are differentiable. And the last part of the methodology will be the decision loss. So these are the concept of smart predict and optimize loss. So basically, it's a very simple concept that you try to quantify the difference between the best solution and the best solution you can get from the predicted cost. And since it's intractable, so we use the trackable version of the SPO plus loss to in the training process. So this is the idea. Sorry. And for the case study, we use London Gatwick Airport. So basically, because Gatwick is like very important, so it stands as London's second busiest airport and the second largest single runway airport globally. And we used around like 47,000 arrival flights from Open Sky Network from this year. And for the metadata, from the weather data, we use Meta. So as you can see from the right figure, actually is based on the map weather algorithm developed by Eurocontrol. So I try to group I can group the weather into 5 classes, which is wind, precipitation, visibility, freeze condition, and dangerous phenomenon. So I will use it in the follow-up study, follow-up analysis. And this is the experiment setup. As you can see, I have this amount of flight, and then I generate this amount of traffic instances out of this amount of flights. So for each instance, we have like 15 flights, and the maximum time window per instance will be 45 minutes. And the area of interest is 50 nautical miles around EGKK. And for typical scenarios, actually it means the ASP, the parameters for the optimization model. Because during the training process, you cannot like change the parameters of the optimization model. That's why we need typical scenarios here to see. This part, I also want to test how it works with like adverse weather. So actually we have the scenario with maximum wind, and the others are the same. Maximum participation, maximum visibility, maximum dangerous phenomenon, and also one with minimum time window. Try to see how the model works. And for the input feature, it will be like this kind of like position status and the operational status of each flight at the entry state of the 15 nautical miles around EGKK. And the output feature will be the transit time. So as I mentioned before, actually we have like 1, 2, 3, 4, 5, 6. We have 6 for one aircraft. So actually we will have 90 inputs and then 15 outputs for one instances. So it becomes this problem. And for time window setting, just it shows here. And for the early bound and late bound, we refer to a ENAC ASP benchmark. And for the training configuration, it's just like very common like machine learning configuration. And for the results, first, I will show the learning curve for the SPO plus and the two-stage approach. So the main, first of all, they are very easy to converge, like within like 0 to 200 iterations. But the main information I want to convey here is the neural network combined with two-stage approach is actually quite struggle here. So compare with other like configurations. So in the following results demonstration, I will only show like linear regression plus two-stage, MLP plus SPO plus, and also linear regression plus SPO plus. And for the next part is the normalized regret distribution. So by regret, I refers to the decision loss. I have mentioned it before. So basically, I just try to visualize the regret distribution during the training process for the test set and see which configuration performs better. So as we can see here, the MLP plus SPO plus, which is the blue line, is actually performs better almost for all the scenarios, except for the visibility scenarios. So we are guessing that maybe we are lacking of this kind of data in our data set. That's why it creates this results. But to further investigate it, those two perform like the better methods, which is the MLP plus SPO plus and the linear regression plus two-stage. We further perform this analysis, which is like the mean cost comparison. So after we train the model, we try to use the test set. We try to use the train model to generate the predicted cost for the test set. So the black line is the first come first serve cost for the true cost, and the orange line is the optimized true cost, also like from historical data. And the blue bar is the MLP plus SPO plus, and green bar is the linear regression plus two-stage. There are two important information wants to convey here. So the first thing is that if I use the minimum time window as my scenario, like the parameter setting for the optimization model, actually MLP plus SPO plus will perform like much better than linear regression plus two-stage. So yeah, this is the first information. The second key findings here is that MLP plus SPO plus actually demonstrates whether responsive behavior with cost ranging from 2,000 something to almost 4,000. Because as you can see, for these four like extreme weather scenarios, actually MLP plus SPO plus will perform like will give you some buffer of the transit time, which has larger costs. But like for two-stage approach, actually it maintains uniform cost regardless the weather. So the takeaway key findings for this piece of work is, the first is the framework implementation. So basically this is the first SPO implementation for this problem. And also we introduced the concept of traffic instances for the multi-aircraft predictions. And the core results is that first MLP plus SPO plus outperforms traditional methods around 43.4% cost reduction in minimum time window setting. And also it has like weather adaptation performance. So SPO shows better overall robustness with strategic transit time adjustments in adverse weather. But the limitation, there are also limitations. So basically during the training process, you need a fixed like optimization model structure, which also limits this method. And another thing is the computational efficiency concern, because now I use like 15 aircraft per traffic instances. So if you increase it to 30 aircraft, actually it runs very slow. So because of the like mathematical model. So for future research direction, I will break it down into 2 points. First is the enhancement. So for the methodology enhancement, actually you can, there is one possible way is like you apply the dynamic parameter updates, which is like still a very, very new like study in computer science that is not stable, but I think it will be like very have potentials. And another way is to improve the regress computation. As I mentioned before, I do simplification for the cost. So perhaps when we are trying to make the regress more like more aligned with the realistic, there will be some more interesting finding. and also explore various neural network architectures for prediction. So basically, throughout the whole study presentations, we know that neural networks works better in this task. So interestingly, so if you just predict like single aircraft in a tabular form, I think tree-based model performs better. But when you are considering more like difficult, more complex scenarios, actually neural networks performs better. So yeah, the exploration will be very good. And also the relaxation for the optimization model and then try with larger traffic instances will be very interesting because now we are still using the exact solution of the MILP mixed integer programming. So it makes it very slow. Not very slow, but it is computational okay. But if you increase the number of flights into like 30, maybe 40, it will become very. And from extension point of view, we need to perform case studies of other airports and also perhaps consider multi-runway system and takeoff scheduling. So yeah, these are basically all of my presentations. So thank you. Thank you for your attention.
Thank you very much. So we have first question, yes?
It was a lot of information, so maybe I lost something. But I think one improvement that I haven't seen at the last slide would be that you are trying to map many points into a weather that is like a single point because they use meter information. So maybe it would be cool to, instead of using single point, using like radar data or like satellite data and trying to use that for the weather information. Because right now you only use a single station, right, at the airport.
Yes. Thank you for your question. Yeah, actually, yes, I just try to use the metadata to represent the adverse weather scenario. So it's not like I'm not using grid data for the weather information. That's one.
That would be a cool addition because that way you would be able to represent really the area around the airport and not just at the airport. So maybe I mean, it would be probably complicated to implement it because you have then many more points to process, but I don't know.
Yeah, I think it would be more complicated, but the procedure might also need a bit changes if we need to really consider the grid data. But that will be definitely a very good direction to explore.
I have a question.
Yeah.
So basically, you come with a methodology that is doing this predict, then you optimize. But I'm wondering you didn't really talk about this kind of comparison you could do with another approach where you would just compute a first solution with the current state of the situation and be able to adapt to modify your situation to have a solution that is robust to changes when things don't happen as you thought they would be. So it's just like, I mean, the other way of doing things is just like, okay, well, for now the sequence would be this one, but maybe, okay, then in the end, this one comes later, so we have to adapt. But like you're doing another approach, but I would like to, some justifications on why this approach and not the other one, and why not, or.
Yeah, I understand. Thank you for the question. So basically, I compare two-stage only with the SPO plus. So two-stage means that I separate like prediction with optimization. But definitely, I use very simple prediction with very simple optimization. So maybe this is not good enough as a complete comparison in this area. But I just try to compare if we use the same core like MLP and then LR and then plus use different kind of framework, decision loss and the predictive loss plus the two-stage, like which will be better. So now it's still like at the stage that we are comparing things that are not that sophisticated, but just new framework and like two things separate, just two things separate and combined together. Just compare these two things.
Thank you. Any more questions?
Thank you for the presentation. I was trying to understand what is the prediction part of the neural network? What would be the output of the neural network?
The output will be the transit time of 15 aircraft. So it will be a vector.
So it's the total duration of
yeah,
each
so
of
the duration
aircraft.
is spent in the terminal
And
area.
based on that duration, you are trying to optimize what the arrival schedule, right?
Yes, yes.
Okay. And what, like, when you say this framework in combining together, essentially is still using the prediction, right? Using the neural network to do the prediction, and again doing the optimization, right? So what is it like? How you combine this together?
Oh yeah, the difference is that the loss function.
Yeah.
So for the neural networks, we use like mean square error, we use mean absolute error, we use different things, cross entropy. We just take that out and then we fill another things in that, which is a decision loss. So the decision loss, we will compute the optimization in each iteration. So that's the difference from the two-stage approach and this like predict and optimize approach.
Thank you, thank you. I will read your paper more to get a better understanding. Yeah,
thank you.
Okay. We have a question online, and then we come back to you. Okay.
Okay.
I'm ready. Okay. Maybe you can read it out.
Yeah. So rather than weather, I believe the bigger influence on Gatwick arrivals is a social and economic bias deployed by the air traffic controllers, for example, noise, flight dispersion, and separation via the holding stacks. I don't know if it's a question.
I don't know if it's a question, but it's a very good comment because I don't know that before. So thank you so much for your comments, and I will try to take a look at these things, study more on the Gatwick.
Thank you very much for your presentation. I believe you use the ADS-B data mainly to check what you are proposing is working properly or not, and to compare with reality. And my question goes in the same direction that the people in Gatwick is telling you, is an operational one. Did you see, at the end, what you propose is a different sequence, and you compute with that sequence. Did you see how far away is this sequence you are proposing from the original one? Also considering that the one that you have on the data is not probably the same that they have on the AMAN, because there are last-minute changes and things like that.
I haven't been able to do this analysis. So now I was just focusing on the like objective value, the total cost. But yeah, I think it will be very important that I implement this, maybe just following up this work to see the difference of the sequence. But I haven't proposed, like I haven't presented here. Yeah.